In this podcast, we'll go through what a conjugate acid or conjugate base pair is, and we'll work some problems. All right, so as we've already established, acids are proton donors according to our Bronsted-Lowry definition. Therefore, if they're proton donors, once they've donated the proton, they become a conjugate base. So a conjugate base, if we were to do the reverse reaction, would be ready to accept a proton from the conjugate acid. Bases, by definition, are proton acceptors. So once they have accepted a proton, the product of that now has a proton that can be donated. It becomes a conjugate acid. So let's look at the example below. We have hydrochloric acid and water forming a hydronium ion and a chloride anion. So we want to start by looking at the changes that happen from reactant side to the product side so we can figure out where that transfer of protons was. So here we see H2O accepts a proton to form H3O+. So since it's accepting a proton, this is my base. Where did it get the proton from? Well, let's look at HCl. HCl lost its proton to form a chloride anion. So that means that hydrochloric acid, shocker, is acting like an acid. All right, so we have our acid donating this proton to our base. Okay, so as we've set up above, our acid forms or produces a conjugate base, and our base forms a conjugate acid. All right, if we were to do the reverse reaction, we would need the chloride anion to accept a proton from the conjugate acid in order to reform hydrochloric acid and water. So the reason why that terminology shifts is because once you have lost your proton as an acid, you are now set up to be a base. You're ready to accept that back in the reverse reaction. All right, so strong acids produce weak conjugate bases. So the table that you're looking at below is not an exhaustive list of all the acids and their conjugate bases. These are just the ones that you're more likely to see in this class. So looking at this table, we see that strength increases going up. So we would assume that this on this list is our strongest acid. Therefore, it has the weakest conjugate base. And we see that strength increases going down our list so that our weakest acid produces on this list the strongest conjugate base out of the ones that are here. Obvious next question, do I have to memorize these acids and their relative strength? No, you do not. If I want you to be able to use this or apply this knowledge, I'm going to give you a problem, I'm going to give you the table, and I'm going to want you to be able to apply knowledge from the table in order to work a problem. All right, so why do we care about the strength of the acids and the strength of their conjugate bases? And the reason we care is because these are equilibrium problems. These are reactions that are reversible. They're in equilibrium, and equilibrium is going to favor the side with the weaker acid. So we've been writing these, and I'm going to write this in a generic equation. We've been writing acid-base reactions, and we haven't paid much attention to these arrows that are on here, but we know that an acid is going to donate a proton to the base, forming the conjugate base with a negative charge, and your base becomes your conjugate acid with a positive charge. What we haven't talked about is that these may not be in equilibrium with each other. So the rate of the forward reaction may not equal the rate of the reverse reaction. So when we say that equilibrium favors the side with the weaker acid, let's take a look at this generic equation and see what we mean by that. So let's say that this is a strong acid, and let's say our conjugate acid is our weaker acid, okay? Well, a strong acid readily donates its proton to the base. It dissociates readily in water, but a weak acid does not readily give up its proton. So the way we would show this with our equilibrium arrows is to show a longer arrow pointing towards the products. So equilibrium is said to be favoring the side with the weaker acid, which in this case we've just arbitrarily identified as being our conjugate acid. So essentially it's getting stuck on that side. And this conjugate acid, being weak, isn't going to readily donate its proton to the conjugate base to reform our products. So it's not going to produce reactants at the same rate as your strong acid produces products. All right, so I'm sorry this writing is super small, but let's work through some problems and see if we can apply what we just learned from the last slide, because it's a lot to take in. So in this first problem, I'm going to identify my acids, my bases, my conjugate acids, my conjugate bases, so that way I can focus on those acids to determine which direction the equilibrium lies and whether I'm favoring my reactants or my products. So in this first example, hydrofluoric acid is my acid and my hydroxide ion is my base. The base accepts a proton, forming the conjugate acid, and hydrofluoric acid loses a proton, forming the conjugate base. So I want to hone in on my two acids, my conjugate acid and my acid. And I'm going to look to my chart. I'm going to determine, strongest being at the top, weakest being at the bottom, whether hydrofluoric acid or water is the stronger acid. So in this case, here's hydrofluoric acid and here's water. So hydrofluoric acid is the stronger acid. Okay, that tells me that water is a weaker acid. That means that equilibrium is going to lie on the product side because it lies on the side of the weaker acid. If you're catching on to this, pause me, do the work, go back, double check if you got it right. If not, we're going to do two more problems together then. Your choice. All right, so for this next example, let's identify again our conjugate acid and our conjugate bases and our acids and bases in general. Okay, so let's look at how things change. This must be my base and this must be my acid because my ammonium ion loses a proton to form the conjugate base, and the chloride ion gains a proton, so it's a base, to form my conjugate acid, hydrochloric acid. So again, we are just honing in on the two acids. We know the equilibrium is going to lie on the side of the weaker acid, so we go to our chart. Hydrochloric acid is here, and the ammonium ion is here. So our stronger acid is HCl. That means that our equilibrium is going to lie on the side of the weaker acid, or it's going to favor the reactants. And we're going to work the last problem the exact same way. Let's identify acids and bases. All right, so this guy is going to accept a proton. That means he's a base to begin with, and he forms this conjugate acid. And this donated a proton to the base, which means it has formed its conjugate base. So again, let's look at just the acids and identify our weakest acid. I put the box around the wrong thing. Hydroniums are acid. Okay, so used color coding, so hopefully this isn't getting too confusing, but there's a hydronium ion, that's one of our acids, and carbonic acid, which is our other one. All right, so our stronger acid is the hydronium ion, which means our weaker acid is carbonic acid, okay? And equilibrium is going to lie on the side of the weaker acid. So equilibrium in this case favors the products.